Hey Chem 100, this is Dr. Ricardo. This is the second video from Chapter 10, and we're going to concentrate on one topic in this video, so it should be shorter than usual. The topic we're going to talk about is electronegativity and the polarity of covalent bonds. Okay, so there is a chart for electronegativity. There's a more, basically covers each element in the periodic table. So if you look, the abbreviated version that I gave you here comes from your textbook, and it really only covers group 1, group 2, and then group 13 through 17. So these are the elements that we're going to deal with 90% of the time. If you want a more complete version that covers all the elements in the periodic table, I posted that. It looks like this. If we were in class, I would hand this version out, and it has every element on the periodic table. So this is also in Moodle. So you see the transition elements are listed as well. Okay, but the book is right in the sense that 90% of the time we're going to be dealing with the elements that are on this chart, and even more than that, we're going to be dealing with hydrogen as the only metal, and typically the non-metals from over here. So carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur, chlorine, all the ones that you see in yellow, plus hydrogen here, are the ones we're going to deal with 90% of the time. Those are the elements that typically make covalent bonds that share bonds. Okay, so that being said, I'm going to start with the notes. And this, again, this should be a pretty short video. Okay, so this is picking up on page 7 of the bonding notes, and it starts with a definition of electronegativity. So we'll start with that. Electronegativity is the attractive force that an atom of an element has for the shared electrons in a molecule. When you think about the bond between H and Cl, the electron pairs are actually closer to the chlorine atom. The chlorine atom is a hog. These two electrons in the shared pair are not shared equally. They spend most of their time closer to the chlorine. The chlorine is not such a nice element compared to hydrogen, right? The sharing is unequal. So what results from this unequal sharing is that the bond is lopsided and kind of reminds me of a guitar pick, where the negative side, and this little symbol here, which is small delta, a Greek symbol delta, means a part of a charge, not a full-blown -1 on this side and a full-blown +1 on this side, but just a partial charge. So maybe this is like 0.2, -0.2 over here and +0.2 over here. So we're not going to worry about what the actual polarities are, what these numbers are, but we're just going to represent which side is lopsided, which side is negative, and which side is positive. Another way to write that is we make an arrow pointed towards the negative side of the molecule. And the cool thing about this arrow is it has a little cross at the bottom, and the cross you can think of as the plus side. So this arrow shows the polarity of this molecule. Okay, that single bond in there is not equally shared. I could redraw this like this, right? And these molecules would have this side being a little bit more negative than this side. So they would kind of line up like sort of little magnets in solution because opposites attract. So the next one that would go next to it would probably have an H here and a Cl here, because the slight positiveness on this side would be attracted to the slight negativeness on this side. This side would be negative, and that's the idea. So you would create these molecules that have poles, a positive pole and a negative pole. And it results from the unequal sharing of the electrons. So this bond in here, these two electrons, or this bond here, is said to be a polar bond. A polar bond because it has two poles, one side being more negative than the other. And what does it result from? That when chlorine and hydrogen get together, chlorine pulls the electrons closer to it. So how are we going to be able to tell which is the negative side and which is the positive side? That's how we're going to use the table I'm going to show you below. Okay, so again, unequal sharing is going to result in a polar covalent bond. It's still a covalent bond. It's still sharing of two electrons, but it's unequal sharing. The electrons are not equally distributed amongst the two. This discussion has everything to do with these two electrons in this bond here, and it has nothing to do with these three lone pairs that are around chlorine. Okay, so there is a scale for this. It's called the Pauling scale of electronegativity, and they're given the symbol En values, for En meaning electronegativity, and they range from the most electronegative element on the whole periodic table, which is fluorine, the one that sucks electrons towards it, sucks bonded electrons towards it more than any other one. It's the biggest hog, right? You wouldn't want to go into business with fluorine because it wouldn't share the profits equally. It would be a hog. Fluorine has a electronegativity value of 4.0, so that's the highest you could ever get. The lowest electronegativity on the whole periodic table is francium. Way down in the bottom left-hand corner of the periodic table, it has an electronegativity of just 0.7. Okay? So it's the least electronegative. Francium is the opposite of fluorine. Instead of being a hog, it's the nicest element in the world. When it shares electrons, it basically gives them over to you. It hardly cares about them. So whenever fluorine is involved in a covalent bond, it's going to have a little bit of a positive charge on it because the electrons are so far away from it over on the other guy who's hogging them up. When fluorine is involved in a covalent bond with another element other than fluorine, okay, it's going to be the hog, so the electrons are going to be, the bonded electrons are going to be closest to it, so it's going to wind up with a negative charge on it, or a part of a negative charge on it. So those are the two ends of the spectrum, okay? In general, electronegativity increases from left to right across the periodic table and decreases from top to bottom as you move down the periodic table. The metals, we can consider them as electropositive, right? They have a tendency to want to just give up their electrons. So they're terrible at holding on to electrons and pulling them towards it. So they're actually almost the opposite. We can think about them, things like francium with the 0.7 as electropositive. Okay? So from 4 to 0.7 is the range. Electropositive things like francium are going to have very low numbers, and very electronegative elements like fluorine are going to have numbers like 4.0. All right, let me show you the trend before we go on and do an example. So the trend is going to come from, if I show you this exaggerated version, not exaggerated version, but let's say complete version of the electronegativity chart. Okay, so you have this in Moodle, okay, and if you take a test in class, I'll always give you a copy of this. So let's see what's happening in the second row of the periodic table as we go across. As we go across, we have more invested in that pair of electrons, right? Because here, these are metals. This one has only 1 electron towards having 8. This one has 2, right? I'm just counting up the valence electrons. This one has 3, 4, 5, 6, 7, and then the magic number, the noble gases would be over here. So neon would be next after fluorine. Okay, so we leave those guys off because they don't get involved in any bonding. They already have 8. So the closer I am to 8, the bigger the hog I'm going to be. Look at fluorine. I'm number 7, man. I got 7 valence electrons. I just need 1 more to get to 8. Give me an electron. Give me an electron. Please, 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 please. Give me an electron. So it's going to be the biggest hog. It's going to go out and steal electrons from anybody because it's desperate to get to 8. It's so close to 8. Oxygen a little less because, yay, 6 is 2 away. It doesn't care as much. Nitrogen, even less than that, 3.0, because it's 3 away from 8. Remember, this is 5. This has 4 valence electrons. It could either go either way. It could lose 4 to get to 2 underneath that, or it could gain 4. So carbon's right smack in the middle at 2.5. Boron even less at 2.0. Beryllium even less, and oxygen. So what's happening as you go across? They have more invested towards their octet, so they're going to hog the electrons more. Okay, why do the numbers decrease as you go down? Well, like I think we've said before with other trends, that these numbers are going to decrease because as the atoms get bigger, these all have something in common, right? They all have 1 valence electron. So as the atoms get bigger, the electron that you're talking about that's involved in the bonding is further and further away from the nucleus. So the energy changes are going to be very subtle because they're so far away from the nucleus. Think about hydrogen. It has 1 electron in the 1s. francium has one electron in the 7s. So this is like Pluto compared to Mercury, right? Mercury is very invested in its orbit around the sun. Mercury is going to have two choices. It's going to continue to revolve around the sun, or maybe someday it goes falling into the sun. No way it's escaping the sun's gravitational pull. Whereas Pluto is so far away from the sun, it really has two choices: stay in its current orbit right now, or maybe someday the gravitational pull gets so weak a gazillion years from now that it just goes off into space. So, very different things. As you get bigger, you're talking about being further and further away from the nucleus. So the energetics gets less important. Things are less dramatic. Removing one of these electrons way down the line is not so critical. Let's take a look at the other end of the spectrum. Why are they going down? Same reason. Further away from the nucleus, the energetics get less, right? If you think about, you had two very small things and you glue them together with crazy glue, they're going to be very hard to pull apart. If I try to glue two giant things like two basketballs or two beach balls, they'll be easy to pull apart. The contact area between the two things is very small relative to the whole atoms. Okay, so those are the trends in periodic table. As you go across, electronegativity goes up. As you go down, electronegativity goes down. Okay, and when I say across, I mean from left to right. Okay, so what are we going to do with these numbers? Well, very simple. We're just going to add and subtract them. Can't be any easier than that. So P is going to be the polarity of a particular bond. So the polarity of a bond is equal to the absolute value difference between the electronegativity of atom 1 and atom 2. So a bond is always taking place. It's localized between two atoms. So you find the two atoms that you're interested in, and you just subtract their numbers. Since you want absolute value, you just need the bigger one minus the smaller one. So let's take a look at a chlorine-chlorine bond. Okay, show you the electronegativity from the chart. Chlorine is pretty electronegative. It's got a value of 3.0. Remember, 4 is the max. Okay, but if chlorine is involved in a single bond with another chlorine atom, this chlorine on the left is a hog, and this chlorine on the right is a hog. So what happens when you put two hogs together and they're fighting over something? They're going to have equal strength. So I take the number for the first chlorine, I subtract the number for the second. 3 minus 0, 3 minus 3 equals 0. The polarity of any bond that's 0, we call it a nonpolar bond. It doesn't have poles, okay? Even though it looks like a peanut, one side of it is just as negative as the other. There's no net difference between the two, okay? So if I just showed you quickly, here's what chlorine-chlorine looks like. You've seen this before. Each one has 7. 6, this one over here, 6 that it owns by itself, plus 1 from the bond, that gives him 7. The one on the left, 6 that it owns by itself, plus the 1 that it's sharing. So we're talking about the 2 electrons in here. Are they shared equally between here and here? Yes, because this guy has an electronegativity of 3, and this guy has an electronegativity of 3. If I'm pulling both sides with the 3, I don't make any headway either way. I get a tie, right? So the polarity of this bond is 0. It's a non-polar covalent. Anytime the polarity comes out to 0, right? Covalent means sharing. Non-polar means equal sharing. One side doesn't hog it up more than the other. Okay, let's do the water molecule. Now, the water molecule, although it has 3 atoms, right, we've done this structure before. The oxygen is totally happy with 8. It's got 2 lone pairs to give it 4, plus 1 from here and 1 from here. Those are the 6 that it came in with. Hydrogen has the other one from here. This hydrogen came in with the other one from here. So hydrogen is happy with its 2-tet. It's a very stable molecule. Okay, and the oxygen is happy with its octet, 2, 4, 6, 8, when I count the ones who are around it. Okay, so what do? I don't double the H because there's 2 of them, because what I'm doing is I'm measuring the polarity of a particular bond. So I have to look up the O number and look up the H number and just subtract them like I did over here. So the O turns out to be 3.5. The H turns out to be 2.1, so I just take 3.5 minus 2.1, and I get 1.4. Well, anytime the polarity comes out to be a number that's greater than 0 but less than 1.7, I'm going to call those kind of bonds polar bonds. They have sides. One side is more negative than the other. Which side is more negative? The side with the higher electronegativity. Oxygen had the 3.5, so these electrons are not shared equally here. They really are closer over to the hydrogen. They spend, to the oxygen. They spend most of their time over this way and less this way. So that makes this side negative and this side positive. Same thing with this one over here. They spend more of their time, right? The sharing is not equal. Spend more of their time over on the oxygen side. So that makes this side negative and this side positive. Well, if that's the way the bonds are going, what happens to the whole molecule? It looks like a boomerang, where the oxygen part is the negative part, and down on the ends, the two hydrogen parts are the positive. And that's actually the way water molecules look. They look like a boomerang with the negative up at the tip, and down on the ends are the positive sides where the hydrogens are. Unequal sharing. Now notice, I didn't multiply the 2.1 for the hydrogen by 2 because I'm measuring the polarity of a bond. Just subtract the numbers. Okay. All right. What's the ultimate case? Oh, if I wanted to draw it with the lines here, all right, I'd make my arrows, or my arrows would go like that, right, to show the vectors, to show which side is positive and which side is negative. The positive side, here's the plus arrow, here's the negative. Same thing on this one. Okay, let's say. And if the two bonds have that, the overall polarity of the molecule will be this side would be the negative side, and down here would be the positive side if I put those two vectors together. Okay. All right, the ultimate is what happens if you get to the point where the sharing is so bad that it's actually not sharing at all. It's actually outright stealing or transferring of electrons. Well, that's what would happen if you did the electronegativity difference between typical ionic compounds like NaCl. So let's look up Na and let's look up Cl. So Na here on my table is 0.9. Chlorine here is 3.0. So to get the polarity of this Cl-Na bond or NaCl bond, I take 3 minus 0.9, which would give me 2.1. Anytime the polarity is greater than 1.7, I'm going to show you that in a second, this sharing is so bad that those two electrons that I could fictitiously think of as being shared between the sodium and the chlorine really aren't shared at all. They really are over there on the chlorine. Now remember, chlorine's supposed to have 7. If it has 8, this guy has a good old-fashioned -1. And this guy had his electrons stolen away, so he has a good old-fashioned +1. So that's what we would expect for ionic bonds. The sharing is so bad that it's not sharing, it's just transfer of electrons like we've been learning the whole year. So anytime polarity comes out greater than 1.7 and 2.1 is a lot greater than 1.7, we would call those ionic bonds. Okay, so here's these notes related to that. If the polarity is less than 1.7, greater than or equal to 1.7, the bond is said to be ionic. And you know what ionic means? Transfer of electrons. If the polarity is between 1.7 and 0, right? So the polarity is less than 1.7 but greater than 0, it has a value like water of 1.4. 1.4 would fall into this range between 1.7 and 0. The bond is covalent. It is the sharing of electrons, but it's unequal sharing. It's sharing where one side does most of the has the electrons most of the time. Okay? All right, so if you look at these rules, we could think about it as a continuum from the two ultimate sides down to the middle. So if you have a polarity of 0, so these are the polarity of the bonds, P. The only way to get a polarity of 0 is to have the same number and subtract it from itself. That usually happens when you have two atoms of exactly the same kind bound to each other. So if I have an oxygen-oxygen single bond or an oxygen-oxygen double bond, I would just take 3.5 minus 3.5 would give me 0. Same thing in the nitrogen molecule N2. 3 minus 3 equals 0. So usually that's what happens. But you could possibly have two different elements that just happen to have the same electronegativity. Like look at carbon and sulfur. If carbon and sulfur make a bond, what's the polarity of that bond? Well, 2.5 minus 2.5 equals 0. It would be a nonpolar bond. Okay, again, just subtract the numbers. Don't double them if there's more than one atom, and don't double them or triple them if it's a double or triple bond, right? If I was doing this one and I said, what's the polarity of this nitrogen-nitrogen triple bond? You look up nitrogen, 3.0. Look up the other nitrogen, obviously it's also 3.0. 3.0 minus 3.0 is a big fat 0. That's all you do. And that's what we'd expect. This is a non-polar bond. Perfectly symmetrical. One side isn't more negative than the other. Okay? Non-polar. Doesn't have poles. Okay? And we have our lone pairs on each side. Okay? Okay, so how do I get 0? Two atoms of exactly the same electronegativity. How do I get 3.3? Well, you remember, that's the biggest difference possible. That's taking 4.0. If francium and fluorine got together, or francium and cesium got together, they both seem to have 0.7, they would be 3.7 would be the difference. That's an extremely ionic bond, even more than sodium chloride. So that would be outright transfer of electrons if you were down on this side. Okay, well, come back from 3.3. If you make it up to and including, this includes the 1.7, up to and including 1.7, you're classified as ionic. If you're lower than 1.7, if your difference between the two atoms is less than 1.7, so something even 1.69, all the way down to 0.1 or 0.05, anything greater than 0, you are a polar covalent bond. One side is negative, one side is positive. Now again, there's a big difference between 1.69 and like 0.05. So the extent, how polar the bond is going to depend on how big a number it is, right? The closer you are to this side, the more dramatic the negative and positive poles will be. Whereas if you had a small difference, it would only be a small difference in the charges, in the polarity, right? We never make it up to a whole +1 as long as we're in this range. We're just a part of a charge, right? Like water here is an example of a part of a charge. Okay, I think that's everything that I have for electronegativity. Let me see if I have one more page. No, I think that's it. Okay, so that's it, 23-minute video. We'll see you for the next one, which should be the last video for Chapter 10.